Hi guys, I'm Nachiket from Nagpur and this is my entry for the Khan Academy India Talent Search. So hope you like it. Hey guys, in this video we are going to look at interference of light based on Huygens wave theory of light. Huygens wave theory was given in 1678. Before this time, the prevailing theory of light was Newton's corpuscular theory. According to this theory, when light is emitted from a source, it travels in the form of a stream of particles, and this stream of particles always travels in a straight line. This theory did well to explain phenomena such as reflection or refraction of light. However, around 1678, several new phenomena were observed, such as polarization and interference. Newton's theory could not explain these observations. However, Huygens wave theory was proposed as an alternative to this theory around this time. According to this theory, instead of treating light as a series of particles, we should treat light as a series of waves emanating from a source. These waves were said to propagate in a hypothetical medium known as the luminiferous ether. This theory could explain reflection as well as refraction equally well. However, it could also explain the newer observations such as polarization and interference. You might ask, what is the difference between treating light as a wave or as a particle? Obviously, there are lots of differences, but the primary difference is the way we add waves versus the way we add particles. When we add two particles, we can just add all their properties together directly. So for example, if this particle has a mass of m1 and this particle has a mass of m2, when we add these two particles, we just get a combined particle with a mass of m1 plus m2, right? But when we talk about waves, it's not so simple, because when we add waves, the resultant wave depends not only on the amplitude of the individual waves, but also on their orientation with respect to each other. If you already know some of the mathematics behind this, you can say that it also depends on the phase difference between the two waves. So for example, if this wave is oriented in this way and we have another wave mixing with it which is oriented in this way, such that the crest of one wave overlaps with the trough of the other wave. So if this one has an amplitude of 5, this one has an amplitude of minus 5, when we add these two together, we get 5 plus minus 5, which is 0. In fact, at every point on the axis, when we add the two waves, we get 0 intensity. So in this case, adding two waves gives us a wave of 0 intensity. However, if the waves are oriented in this way, such that they completely overlap with each other, in that case, if they have an amplitude of 5, then the resulting wave will have an amplitude of 5 plus 5, which is 10. So we get a huge monster wave, which is just a combination of these two waves. This difference in the way we add waves and particles is the primary reason why we see interference in light. So guys, I have assembled a do-it-yourself kit to show an interference pattern at home. This is something not many of you guys might have. It's an antique. It's a CD with two wires stretched through its hole in the middle. Well, I say wires to sound fancy, it's just two pieces of hair. And this is a regular laser. What I'll do, I'll shine this laser through these wires and onto the screen. And then I'll dim the lights and hopefully you'll be able to see the interference pattern. So this is the interference pattern of light. This pattern is extremely significant because it was the first time in history that anyone had dared to even think that the almighty Newton could be wrong. But he was wrong, because if you still insist on following Newton's theory of light, then all you should expect to see is two slender shadows of the wires on the wall surrounded by uniform brightness everywhere else. But then how can you explain the alternating bands of brightness and darkness on the screen? This was the first indication that a new theory of light is needed, and Huygens was the person to provide it. So now let's see how we can use the wave theory of light to explain this pattern. So I'll just draw a quick diagram of our setup. This was our CD, and this wire divided the hole in the CD into two different slits. And this was our laser, and this was our screen. So if we consider Newton's corpuscular theory, we should have two different streams of particles meeting the screen at this point and this point respectively. So what we should expect according to Newton's theory is a bright spot here and a bright spot here and darkness everywhere else. However, what we did observe was an alternating series of bright and dark spots. We can explain this using Huygens wave theory. So let's consider light to be a wave emanating from the laser, and it reaches the slits at the same time. As it reaches the two slits, it actually splits into two separate waves. That means that the light that we receive on the screen is the mixture of light from these two different sources. And as we just saw, a mixture of two waves is not always equal to the direct sum of their amplitudes. Since the sum of two waves or the mixture of two waves depends on the orientation between the two waves, we should have a different kind of mixture at each of these points. So how do we figure out what kind of mixture we will have? For that, let's take a look at the following demonstration. Here I've tried to give you a physical demonstration of interference. So what I've done is I've taken two identical plastic strips, drawn two identical waves on them, and stuck them on two different points on a thermocol sheet. So these two toothpicks denote our screen, while these two plastic strips are basically the rays of light coming from our two slits. Now if I take this point, which is the midpoint of the screen, you can see that at this point the two waves overlap completely. And if you think back to what I told you about mixing of waves, you'll remember that at this point the resultant wave will have twice the intensity of the constituent waves. At the same time, if I shift my point over here, at this point the two waves are exact mirror images of each other. So at this point, if you again recall what I told you about wave mixing, at this point we should get zero intensity because these two waves cancel each other out entirely. So if we shift our point gradually along the screen, you'll see that we have a bright spot here, a dark spot here, a bright spot here, a dark spot here, and again a bright spot over here. So that explains the phenomenon of interference. So guys, that was my video. I hope you enjoyed it. It's my first video on YouTube, so I don't have a signature outro yet. So I'll just go with please like and comment, and thank you for watching.